invariant metric on the CLE form.
It's a pleasure to be here. First, I want to thank Hal for giving the first part of what is essentially a two-part talk. At the end, she mentioned this question of whether you can show in the exploration process on CLE4 whether the loops determine the exploration, and therefore whether you can construct a conformally invariant metric on CLE4. We'll show that the answer is yes. But before I get into the proof, I first want to give a bit different perspective to give some motivation, although I'll stress that what I'm going to say is not rigorous and we haven't made a connection with the story. So, if you look at CLE kappa in the regime where the loops touch one another, there's a very natural metric you can put on the loops where you just declare two loops to be adjacent if they touch, and then just consider the graph metric on the resulting graph. All right, so these loops don't look very realistic, but you get the idea. So the points of the metric space are going to be the loops, and the distance we're interested in is the graph distance. Now, in this regime, the metric is manifestly conformally invariant because, of course, it's a direct function of the loops. The loops are conformally invariant. The touching relations are preserved under conformal maps, so in this regime, you're going to have a conformally invariant metric without a lot of work. So now, what about between 8/3 and 4, not including 4? So here you have to think a bit more about what you want to do, because of course the loops don't touch. And one simple way to do something similar is to fix some epsilon greater than 0 and consider two loops to be adjacent in the graph associated with the parameter epsilon if there are points on the loops which are within epsilon of one another. So you might end up with something like that. And so then, of course, the question is what happens as epsilon goes to 0. And the conjecture is that so the distance in the graph metric associated with epsilon from one loop to another goes something like, well, I'll put the constant first. Some constant depending on gamma 1 and gamma 2, and also depending on the domain omega, times epsilon to some power minus alpha. So one natural thing to do is interpret this, to divide by epsilon to the minus alpha to cancel this epsilon-dependent part, and interpret the remaining constant as a notion of distance between points. Between loops. But what you'll notice about that is that if you scale the whole picture by some quantity lambda, then this metric is the same except with lambda epsilon balls instead of epsilon balls. So essentially, what happens is that you end up with an extra factor of lambda to the alpha for this constant if you blow the whole thing up by some factor lambda. Which means that under a more general conformal map, what you would expect is that there's a power of the derivative of the conformal map accounting for this scaling. So in other words, in this regime, we had conformal invariance, and in this regime, we expect a conformal covariance. And so then the remaining regime, of course, is kappa equals 4. And what happens there is, I guess, a bit different from both of these pictures. It's different from this one because the loops don't touch. But it's different from this one because instead of an epsilon here, you get a log factor, log 1 over epsilon. And again, this is just conjecture. But it means that if you scale everything by some factor lambda, then you just get an additive error which doesn't contribute anything, and the epsilon goes to 0 limit. So this constant is going to be the same under scaling. So that gives you some sense that there's a reason to believe that there might be some conformally invariant metric on CLE4. So that's what we're going to talk about. I'm not sure. There must be some precise form of it, but I don't know what it is. Okay, so as I said, we're not going to be able to get into this part of the story. It's a goal, but we don't have that yet. So how do we come up with a conformally invariant metric? Well, what we do is we start with this exploration process or growth mechanism that you heard about this morning. So I'll use growth mechanism and the exploration process interchangeably. So what does it have to do with the distance? Well, the growth mechanism gives you a time parameter for each loop, and we're going to interpret the time parameter as the distance from the boundary. So so the time parameter associated with each loop is the distance from the boundary of the domain. Okay, so that gives you a notion of distance from the boundary, but of course what you really want is to be able to measure the distance between any pair of loops, not just one loop in the boundary. So how do we deal with that? Well, one idea is to use a shape for the outer boundary of the domain that has the property that we can invert the picture. So apply 1 over z minus z naught, where z naught is some point that gamma 1 surrounds. And that will flip gamma 1 to the outside. And then if we've done a good job of choosing the outer boundary of the domain, then this inversion will give us something that has the same law as a CLE4. And then we can just do the same thing again. We can explore from the boundary in that picture. So what outer boundary would have the property that when you invert it, you get something that has the same law as what you started with? Well, we're going to use a result of
Sam, if this is conformally invariant, does it matter what the outer boundary is?
Well, I mean, if you start with an outer boundary of a disk, and then you invert it, now you've got one of your loops is a disk on the inside. And so what does it mean to explore from, what does it mean to explore the region inside? I mean, actually you can make sense of it, and there's a way of doing that with sort of bypassing this step. But it's not clear a priori, how to interpret your picture if you've got a round ball in there instead of all of the loops being CLE type. So what we're going to do is use a theorem of Werner and Kampainen, which says that if you look at CLE4 in a large disk and you take the size of the disk to infinity, then you end up with a whole plane CLE4 process that has the property that each loop surrounding the origin in that process has the same shape in law. In other words, There's a scale factor that controls where they are, but the up to scale factor of their shape has the same law. So, and we'll also need a part of this result that says that, in fact, this process is Mobius invariant. So you can invert the CLE4, and it's the same thing. All right, there exists a whole plane CLE4 process. It's invariant under conformal transformations of the sphere. With the property that the shape of each loop is the same. Where by shape, I mean equivalence class under scaling.
So this is a nested?
Right. So the picture to have in mind is that we started with a disk, and then we sampled the loops surrounding the origin, as well as the other ones, but they're not so important for what we want to talk about. And then the loops surrounding the origin inside of that one, and so on to infinity. And then you somehow zoom in as you do this process, so that this outer boundary goes away to infinity, and what you end up with is some sort of stationary loop shape with loops inside of it, and then loops also, so they're going onto 0 there, and they're also going out to infinity here. So it's nested. Okay, so now the thing about that that's nice is that if we choose the outer boundary of our domain to be a stationary loop, then it has the property that if we want to measure the distance between two loops, we just choose a point inside of one of them, send that point to infinity. Now it's on the outside, and the whole picture has the same law as what we started with. A stationary loop on the outside and a CLE4 inside. All right, so we define the distance from gamma 1 to gamma 2 be the exploration time when gamma 2 is discovered, starting from gamma 1. Now, we've got a lot of exploration somehow in the picture now, one starting from every point, or from every loop rather. And I haven't specified how they're coupled together. And of course, the final answer is going to be, it doesn't matter how you couple them together because they're all determined by the loops. But just for the sake of having a concrete definition now, let's say that they're sampled independently given the loops that you see. Conditionally independent, I should say, given the loops.
So are you defining your distance function on the whole plane CLE?
I mean, if you want, you can, that's fine, but I just have in mind still one stationary loop and then a simple CLE inside of it. Because the Mobius invariance of the whole CLE also tells you that this picture is inversion invariant, just this piece of it where you take one annular region inside. Okay, so I haven't shown you that this is a metric yet, even if you believe me that the loops determine the exploration process. And really the way I want to set this up is, instead of talking about a distance function directly, I want to axiomatize the notion of a metric space in terms of the metric balls rather than in terms of the metric. So the axioms of a metric space, when you cast them into the language of closed balls, so we're going to let B sub r of x be the closed ball, or play the role, I should say, of the closed ball. I mean, it's going to be a fundamental object in what we're describing, but you should think of it as a closed ball. So instead of 3 axioms for a metric space, what we get is 4 axioms. The ball of radius 0 contains only the point, so that's identity of indiscernibles. It's clear that metric balls should nest, and that one's going to be pretty obvious. It's not too important for us.
R is less than S.
Right. R is less than S. The third one is symmetry, which is not clear from this definition. So I said we start at gamma 1 and explore until we hit gamma 2, and we call that the distance. Well, it could be that if you start at gamma 2 and explore till you hit gamma 1, that it's different. And we need some, in order to write down what symmetry should mean in terms of the metric balls, we need some way of describing distance in terms of the metric balls. So we're just going to use this shorthand, essentially the same thing as what we have there. The biggest value of r, it should move from the edge. Such that y is not in the ball of radius r. So the symmetry axiom using that shorthand is just what it is for a regular metric space. And then the triangle inequality, you write in a little bit different way that we're going to use. So if r plus s are real numbers less than the distance from x to y, then the ball of radius r is centered at x, and the ball of radius s centered at y are disjoint. So that's the triangle inequality. Now, if we look at 1 and 2 using our definition, our axiomatic metric balls, then they're trivial, so we'll skip past those. And what we'll show is actually a single condition that will apply 3 and 4 together. So we're gonna call this the tangent balls condition, and it's going to imply 3 and 4. So if the tangent balls condition says that if you have 2 points, x and y, and you choose some radius r for the ball centered at x, then and then you make the radius of the second ball flexible and sort of grow it until it hits the first one. So sup of t such that then this is constant, okay, for r up to the distance between x and y. Okay, so again, we're going to call that the tangent balls condition, and where should I go? The picture that goes with it is just this idea that if you have x and y, you have some ball of radius r and some ball of radius s, and you take the ball of radius r and maybe you shrink it down and get some new radius r prime, and then you increase the radius of s to match, and you get s prime. Then r plus s has to equal r prime plus s prime. So this is not a condition that's satisfied in general for metric spaces. We couldn't sort of substitute that in for these last two, but it's gonna be true for us. And if you have it, it's a very straightforward exercise to show that it implies these last two. And this idea, the geometry here, we're really going to take advantage of this picture, this idea of sort of growing the ball in one direction and shrinking the other one so that it remains touching. All right, any questions so far? Okay. So the next thing I want to talk about before I start writing down the proof is annulus CLE exploration. So the definition of annulus CLE is the following. If you have an annular region A, so if A is an annular domain, then we sample a Brownian loop sup in A, just like you would do in a simply connected domain. Except the difference is that it's possible that the Brownian loop sup will make a chain of loops that goes, a cluster of loops that goes around the inner boundary, and we don't want that. So we sample a Brownian loop sup in A conditioned on no cluster surrounding the inner boundary. Okay, and then the outermost clusters, the outermost boundaries of the outermost clusters in that picture are our annulus CLE. Okay. And the first observation I want to make about annulus CLE is that if you take some compact hull connected to the outer boundary, and I'll use compact hull in this context to mean a compact set with the property that its complement in the annulus is doubly connected. So I don't want it connected to the inner boundary at all. So some annular region, and that's my compact hull K. And the fact is, for annulus CLE, the law of the set of loops that touch K is absolutely continuous with respect to the law of the loops that touch K for a disk CLE, so if this inner boundary weren't there. Okay, fact. absolutely continuous is way too long to write. So the annulus C loops hitting K are absolutely continuous with respect to the disk CLE loops hitting K. And the reason is essentially that once I sample, so I've got my Brownian loop soup in A. Once I sample the loops hitting this set, I could fill out and get a Brownian loop soup in the disk by sampling the loops that also hit this disk. But there's always going to be a positive separation between the loops, the union of all the loops that hit K and this inner piece. So there's always some positive probability that none of the loops, the Brownian loops contained in the disk that hit this inner domain will also hit this part. And in that case, the loops are going to be the same. These loops are going to be the same. Of course, the ones on the inside will be a bit different. But the point is, if you stay away from the inner boundary, the law of what you get is absolutely continuous with respect to disk CLE. So let's call that fact 1. Fact 2 is that if you want to explore up until the hitting time of K complement, then you don't need to see any loops that don't hit K. And this picture is not great for that because the hitting time of K complement for the disk so this is for a disk exploration. What I'm going to have to do is choose a K that doesn't get close to the boundary here in order for this to be interesting. But the point is that for a disk exploration, the law of the exploration up to the hitting time of the disk without K is conditionally independent of the exploration after that time, given the loops that do hit K. All right, what was the point of all that? The point is that if you have an annulus CLE and you want to explore it, maybe I should read that again, people are trying to read it. For a disk exploration, the law of the exploration up to the hitting time of the complement of K is conditionally independent of the subsequent exploration given the loops of K. Sorry, given the loops hitting K. So the point of these two facts is that if you have an annulus CLE, what you can do is take a compact set K, you can even choose it to sort of hug the inner boundary, and you can explore up until you hit the complement of K at least, by just pretending that what you see is actually coming from a disk exploration, and just explore from the conditional law of a disk exploration given those loops that you see. And this part is telling you that you don't need to see any loops ahead of you. You just need to see the ones that hit K. So that means that we can take a sequence of compact hulls increasing to the whole annulus and explore, I keep losing my eraser, and explore up until we hit the inner boundary of the annulus. So take a sequence of compact hulls approximating the annular region A and stitch together explorations of these KNs to get an exploration of A. Yep.
What is K here? Is it in the middle or?
Well, so K is a
Something attached to the boundary?
so for example, if A is just a regular annulus, so all the space between R and 1, then one example of something you could choose for K sub n would be all the Z's just sort of a little bit away from the boundary, and then let n go to infinity. So you're approximating your annular domain from the outside in. Usually you think of these compact hulls as sort of like this one, just kind of sitting on a piece of the boundary. That's not really what we want it to go all the way around, because otherwise this second statement is trivial. You don't explore it all before you hit the complement.
You were a bit confused about fact 2, so can you just explain a bit? Can you color the set K? Which one?
Sure.
So when you mean given the loops hitting K, which you mean all the loops hitting K, or?
Right, all the loops hitting K. Keep alternating between CLE loops and so you get to see all these loops that hit K. And the point is that if you want to explore up until you hit K, then you don't really need to see what's inside. And it's essentially, the proof is trivial from the definition, because one way to sample the exploration process is to just first explore until you hit K, and then sample the rest of the loops inside, and then keep exploring. Right, and then it's straightforward. Right, and the point of all this stuff is just to get an exploration process in an annular region that goes all the way up to the inner boundary. And the main way in which we're going to use this idea, and I'm not going to give the details, but it's pretty straightforward. The upshot is that if you have any sort of random compact set inside your CLE that you obtain by exploring somehow from the inside out. So maybe it's the loop surrounding the origin, or maybe it's the loop surrounding the origin plus some more loops on the outside as you grow the exploration process in some way. Any random set obtained by taking any random simply connected set inside a disk has the property that, conditioned on that, the exploration up until you hit it is an annulus exploration. So for any random set explored inside out, I should use a different letter than K because it's playing a different role. C. Right. So any random set C explored from the inside out conditional law of a disk exploration up until the time when it hits C is given by an annulus exploration in the complement of C. So yeah, so random set here, yeah, what do I mean? The idea is that it's coupled with a CLE. All right, so for example, you can take a CLE, just a regular CLE4 in the disk, consider the loop surrounding the origin, and then ask yourself, what does the exploration look like outside that, conditioned on the loop surrounding the origin? And the answer is it's just an annulus exploration in that region. Okay, and to prove this, you just take a countable set of a random set, a countable set of set C, and then you have some continuity argument to extend it. All right, so I think I said some confusing things here. Are we all clear from this point? Okay, so all right, now I'm ready to get into the proof. So
by the way, you say your definition of annulus CLE at this point is not yet known to be conformally invariant if you were to change the inside loop shape.
right, there's
At least at this stage you haven't shown that, is that right?
that's right. Yeah, there's not as much in this definition as you would maybe like. It's not necessarily this notion of annual CLE is not necessarily, this notion of exploration is not necessarily invariant under all conformal maps of an annulus.
If you change the shape of the inside loop, it may change the way you explore outside it.
Yeah, so the exploration may change, but the law of the CLE.
Right. Yeah, that's right. The annulus CLE is definitely invariant under all conformal maps, but this CLE process, exploration process, is only invariant under conformal maps that extend to conformal maps on the disk, as far as we know. I mean, I guess that's probably the way it is. Okay, so all right, so we're ready to prove the main theorem, and the first thing I want to do is conformally map everything to a cylinder just for purposes of drawing the picture. It's going to be easier to reason about what's going on. And bear in mind that what I'm ultimately driving at is this sort of tangent balls condition. That's going to be the once we prove this, then that gives 3 and 4 in this metric space axiomatization, and then we're done. So what I'm going to do is start with a stationary loop, and then I'm going to explore in the region to the right of that, just using a regular CLE for exploration in the disk. So I explore loops that are not surrounding the origin for some exponential amount of time. And then at some point, maybe my frontier looks like this, I discover the loop surrounding the origin, which will look like that. So I get that along with all the CLE loops on the inside, the ones that I discovered, and then there were patches that I jumped over because I was targeting at this end of the cylinder, and I'm going to fill those in too and get a full CLE in there. And what I'm going to do is define a couple of measures on configurations. So mu1 is going to be the picture you get when you first sample this. Let me give some notation actually. So this forward exploration process here that I just uncovered, I'm going to call it d sub s, where s ranges from 0 to capital S, which is the full duration, how long it takes to discover the inside loop. So mu1 is going to be the law that you get by first doing this, and then actually weighting the probability measure. So it's going to be, mu1 is going to be a probability measure. And we're going to weight by capital S. So we sort of extended it by exploration time in this direction. Weight by capital S. And I want some more structure. What I'm going to do is sample sigma from the uniform measure from 0 to S. So it's just a uniform random time in between here and here, exploration time.
Sorry, what's the measure that you weight?
Weight.
Stationary measure on these.
Well, so yeah.
And what's the measure on? It's on just this annulus of loops or the whole cylinder, or
So maybe I'll call mu the law of this picture. So again, I just took a stationary loop, then I explored explored the region to the right using a regular disk exploration process, and that's it. So this is just the law of an exploration process to the right of the stationary loop. So so I'm going to weight this probability measure mu by S. All right, and then I'm going to, as I said, add some extra stuff here. I'm going to choose a particular contour, exploration contour, partial d sub sigma. And then I'm also going to choose, so I'm also going to sample an exploration of the same annulus CLE. So this bit in between these two white loops is an annulus CLE. So I can also sample an annulus C exploration from right to left. And I'm going to do so in a manner that's conditionally independent of the forward exploration given the loops. So this is very much the same kind of idea in Dubeda's original paper on showing that the SLE4 is determined by the Gaussian free field. Same idea. So we have the loops, we have this forward exploration, we sample reverse exploration conditionally independent given that one. And we're going to call that reverse exploration E, so E sub t. And its total exploration time is going to be capital T. Right? And then we're going to choose tau. So that it touches. So we're imagining this picture now. We want to have these metric balls touching so that we study something like this. So sigma is just a uniformly contour selected uniformly at random from exploration time, and then tau is chosen in some perhaps complicated way depending on sigma so that they're touching. So then the next thing I want to do, well, okay, that's mu1, and then I'm going to also have mu2, which is going to be the same thing, except with forward and backwards reversed. So I'm going to choose tau now uniformly between zero and capital T, and I'm going to choose sigma so that it touches. And I'm also going to weight by capital T instead of capital S. Okay. So is this definition clear? mu1 and mu2. Okay. The claim is that if you restrict your attention to the exploration up until sigma, forward exploration up until sigma, and the reverse exploration up until tau, so just to the collision time, then actually the laws of mu1 and mu2 are the same. So I'm going to write capital omega for the whole annular domain. And then I'm going to write gamma for the CLE loops on the inside. And then I just want to look at these explorations up until they hit. You don't get to see anything more than that. Okay, and the proof, I think it's maybe a little surprising. It's the part, I think this is the part where the magic happens.
Excuse me.
Yes.
What is gamma?
So gamma is going to be the CLE loops on the inside, so the green ones. And omega is going to be the whole domain. I mean, I just mean the stuff other than the exploration, really. Okay, so I'm going to start the proof by doing something completely different, and then we'll make the connection. So here's a different configuration. I'm going to start with a stationary loop, and then I'm going to explore the region to the right with an annulus CLE, a disk CLE exploration process, until at some point I discover the loop surrounding the origin. And then inside this new dotted line, I'm going to continue exploring to the right until I discover another one. So maybe this is the frontier at the discovery time. And then that's the next loop that I find. And then I'm going to ignore this one. Don't care about that one. And what you'll see is that this sort of looks like the same kind of thing. I mean, we have a stationary loop, we have a figure 8, and then another loop over at the other end. And what we're going to argue is that actually this really is the same. The marginal law under mu1 of that tuple, so the whole configuration up to hitting time, is actually the same as this. And then we're going to use the fact that this picture is inversion invariant. So the fact is not apparent from the construction because we constructed it going in this direction. So that picture is inversion invariant. And this is going to be in a paper with a paper by Manglu Wang and Hao Wu that's a follow-up to the paper that's already on the archive where they do the whole level line story that she talked about this morning in a domain. They're going to do the same thing in the whole plane. And the reason that this has something to do with the Gaussian free field is essentially that this is just a snapshot of a small section of the Gaussian free field. And these really are precisely the contour lines that go around the origin. So you can explore them. You can imagine you got your Gaussian free field there. It's static, and you can explore it in either direction. And in one direction, you get a CLE loop, and then here's the next CLE loop, and then this is the frontier before discovering this one. And then in the reverse direction, this is a CLE loop, this is the next one, and then this is the exploration frontier before you discover the one after that. So this is the only place where we're using the Gaussian free field story, but it's pretty critical because it shows that this picture is inversion invariant, and that finishes up the connection between mu1 and mu2. But we still have to say why this picture is the same as this picture. And we'll do it one step at a time. So the left loop is stationary in both pictures. So far so good. And then in this picture, this loop, the loop number 2, so I should give them names. Loop 1, loop 2, loop 3, loop 4. Loop number 2 and the whole exploration from L1 to L2 is obtained by just exploring disk exploration, using the dynamics of a disk exploration for an exponential amount of time from loops that do not surround the origin, because that's the first one that surrounds the origin. Okay, so that's clear from this point of view, and maybe it's less clear over here, because first we went all the way, and then we backed up some, to find this number sigma that was chosen uniformly from this distribution. But the thing is, capital S under mu has unit mean exponential distribution. And if you weight a unit mean exponential random variable, what you get is the same as the sum of two IID copies of a unit mean exponential. So in fact, both sigma and capital S minus sigma are independent unit mean random variables. So this picture from this loop up to partial d sigma is also given by just a disk exploration using loops not surrounding the origin for an exponential amount of time. All right, now we need to skip from 2 to 4. So in this picture, if you want to say what the law of loop 4 is given loop 2, well, it's just the next CLE loop in a whole plane CLE. Because if you look at this process from right to left, as I said, that's a CLE loop, and that's the next one. And as we discussed earlier, this result of Vernon component shows that the whole plane CLE is inversion invariant. So if this is a CLE loop, then that's the next one. Right? So it looks strange, but it really just follows from this symmetry relation and this Mobius invariance result. And then here, similarly, the way you get this boundary is, the way you get this loop from this one is that you explore, capital S minus sigma units of time, which is an exponential random variable independent of the past. And then you draw a loop surrounding the origin. So this, from loop 2 to loop 4 here is also just given by the next loop kernel, if you will. And then finally, the exploration in between L4 and L3, here it's clearly given by an annulus CLE exploration process, again viewing the Gaussian free field as an exploration from right to left. And here it's true as well, because this exploration up to time d sigma, up to time sigma, is explored from left to right. So if we ask what's the conditional law, if we ask what's the law of the annulus exploration all the way to here, stopped upon hitting d sigma, what we get is just an annulus exploration in here. So that concludes the proof of that claim. Okay, I should have written more stuff, but that concludes the proof of that claim. And then finally, to wrap it up, what we're going to show is that the mu1 law of S and the mu1 law of T are equal. And that proves that S equals T, actually, because this is the mu1 law, this is the mu law of S squared, since mu1 is just weighted by S. So this is the second moment of S, and this is the mu law of S times T for the same reason. And by symmetry, the mu of s squared is the same as mu of t squared. So if we have this result, then we have equality in Cauchy-Schwarz, which implies that s equals t up to some constant, and then by symmetry the constant has to be 1. So I'm going to omit that argument. Hopefully it's clear. And I'm quickly running out of time. But essentially, the pieces are in place because we know what the mu1 law of s is. It's just the second moment of a unit mean exponential, which is 2. So really, all we need to show is that mu1 of t is 2. So even if we weight by left to right exploration time, the mean of the right to left exploration time is 2. And the reason is that maybe I can afford to write this down. How much time do I have? Can someone? 2 or 3 or 4 minutes. Okay, I think that's fine. Constantly losing track of my eraser. Oh, let me say one more thing before I say this because it's more important. Once you know that s and t are almost surely equal, then that actually gives you this result because by this first claim, sigma and tau are equidistributed. And sigma is uniform, so that means tau is uniform. But also tau is a function of sigma. So you have a uniform random variable and then some function of it which is also uniform. So that means that function has to be a linear function, which must be the identity. So actually, once you have this claim, and you know that capital S equals capital T, then you know you have this. You know you have this business where if you shrink this radius and increase this one to match, the resulting sum is the same. Okay, so we know that mu1 of S equals mu of S squared, which is 2. And to calculate mu1 of t, so this is the expected total amount of exploration time from right to left, we begin by writing t as tau plus t minus t. Sorry, tau plus t minus tau. It's hard to say. And then we're going to condition, use the Tower law and condition on some sigma algebra, which is going to be just the sigma algebra generated by the exploration up to collision time. So it's this business that we showed is the same in first claim. And then the thing to notice is that tau is measurable with respect to f. You can see how much time it's taken to find the breaking point. So this just becomes tau. So this is mu1 of tau plus mu1 of the conditional law of the remaining time. So you ask how much time has it taken so far and what's the expected amount of time it's going to take after that. And then this is 1 because the law of tau is the same under mu1 as under mu2, and under mu2 it's just an exponential random variable, so that's 1. And then this part, it actually requires a bit of finesse, and I'll have to skip some things, but the main point is that it's sort of clear that the expected amount of remaining exploration time after you hit that purple interface should just be the expected amount of time for an annulus exploration to explore this remaining CLE. I wish I could reach it. So there's some CLE in between, annulus CLE in between this purple one and this white one. There's some expected amount of time it takes to explore such a thing, and that should be the conditional law of the amount of remaining exploration time. So maybe let's call this function as a function of the annual CLE G. Let's call the CLE in that space between the purple and the white. Let's call that gamma prime. This should equal something like that, and you could prove it. As I said, it's an argument. I'm cutting it out. But the point is that because mu1 and mu2 are the same, the law of this CLE gamma, the marginal law of gamma prime, is actually just gamma prime along with the left edge is actually just a disk exploration in the region to the left of the purple line. So that means that this should be just the same as it is under mu2, which is the amount of exploration time it takes to explore disk exploration is 1 on average. So you get the same thing. All right, that's all I have.
Are there questions? Remarks? So,
Are you sure the last line is okay?
I was a little bit pleased with that, I'm not going to lie.
so you get the. I mean, when you do one exploration in one direction, you have a natural sort of candidate for the geodesic, which are sort of the chain of loops that you can follow, that you're hooked up. If you look backwards, sort of where you are hooked up. So here, basically, this proves that this chain of geodesic is the same in both directions.
Yeah, I guess so. I mean, the point is that if you have the full footage of this whole exploration process and you roll this white process forward and the purple one backwards to match it, then there are going to be times when it sort of jumps over a loop. So this business of them actually touching at a point is just what happens at a typical time. I mean, at some point they have to hand off a loop from one to the other. And yeah, I guess. Yeah, it shows that the geodesics would be the same from the two directions. Yep.
So maybe I didn't follow something early on, but so you've defined the distance between two loops in the, let's say, in the whole plane CLE. Have you actually defined the distance between all pairs of loops?
Well, so the point is that once you have the whole CLE sampled, this argument. Yeah, so that's true. I didn't state the concluding part of Dubedow's argument, which is that if you have two quantities which are sampled conditionally independent given something, and they end up being equal to each other or just determining each other, then actually they're both determined by the underlying thing that they were depending on. So this shows that if you just see the loops gamma, you know exactly how to explore. There's no more wiggle room, which means actually that in this coupling between explorations centered at any arbitrary loop, there's a very natural coupling, which is just choose them the only way that you could choose them given the configuration you see.
Something I didn't follow is like in your picture here you like 4 loops. Some of them come from like actual loops surrounding the origin, right? But some of them are some more boundaries of expression process.
That's right. Well, I mean, in some sense,
you said they're the same, right? You said that you can't really distinguish actual.
Right. I mean, the point is that if you explore from this direction, then all the left ones are real CLE loops, and all the right ones are frontiers right before you discovered the CLE loops. And if you explore from this way, then all the right ones are CLE loops, and all the left ones are exploration frontiers right before you discovered them.
Right. So the law of an expression frontier is exactly the same as the law of CLE loop.
Right. Right. Yeah, that's one implication.
That you see on the GFF. That's it. How do you?
I mean, yeah. You just have to see it from the GFF. You explore one way, realizing the right ones as CLE loops, and then you explore the other way. And then you at some point you have to say that actually the explorations from the two directions coincide. There's the GFF sitting there. Doesn't matter which end you started exploring from. You found all the same stuff because it's all just sitting there for you to find.
Any other question?
Thank you, speaker again.